This is a solution video for the Bernoulli trials probability worksheet. The first question asks us what 4 conditions we need to meet in order to be able to use Bernoulli trials as a method for solution. You need to know this because you can be asked this in your exams. There must be a finite number of trials. Each trial should have 2 possible outcomes, and we consider these as success and failure. So for example, if you had an archer shooting at a target, success might be hitting the target and failure would be a miss. Trials must be independent. This means that the result of one trial mustn't affect the next. And probability of success or failure must be constant. So, for example, going back to the example of our archer, there must be the same probability of hitting the target each time. So let's look at how to apply Bernoulli trials then. In question 2, we've got a bag containing counters. We want to select a counter 5 times, and each time you'll note that we replace it. That's important in this question because it means that each of the trials is independent as a result, and the probability of our success or failure is not going to change over the course of the question because you'll always have those 5 counters in the bag. We want to find the chances that a green counter is selected 3 times. First, let's note our formula. So our formula for Bernoulli trials is n choose r, p to the r, q to the n minus r, and it's important that we understand what each of these stand for. N is the number of trials. In this case, I want to select a counter randomly 5 times, so there's 5 trials, n equals 5. P stands for success. In this question, the focus is on selecting a green counter, so we'll consider a green counter to be success. Looking at the bag, there's a probability of 2 and 5 of that. Q is failure, so that's just going to be 3 and 5. And R is the number of times we want a success, so we want a green counter to be selected 3 times. Note that P and Q should add up to 1. So the probability of selecting a green counter 3 times is 5 choose 3 by 2 over 5 to the power of 3, so that's my success probability, and I want that to happen 3 times, by 3 over 5 to the power of 2, so I want failure to occur 2 times. Again, notice how the 3 and the 2 here add up to the 5. When typing this into my calculator, I'm going to use the NCR button for the 5 choose 3. Just remember to put in all the brackets as well as you type things in. Okay, so I'm ready to type it in. So I'm going to put in open bracket and then 5, shift the division symbol to get my C, choose 3, close bracket, 2 over 5 to the power of 3, and then 3 over 5 squared. So my probability is 144 over 625. I'm absolutely fine leaving this as a fraction, unless of course the question requires me to give it in decimal form. Question 3 is the same type of setup. Basketball player trying to take a shot. We want 4 successful scores out of 7 shots. Noting the formula first is a good plan. I'm going to identify each of my values. Note that I've chosen to write P and Q here as decimals. I fill my formula in, and I note my full decimal answer. I wasn't asked to round off in the question, so I won't round off. On to question 4, which is about a die being rolled. I'm going to note my formula. Let's just think back for a second as to why, again, Bernoulli is appropriate for this. There's a finite number of trials. I'm only rolling it 12 times. The trial has 2 possible outcomes, success and failure. Well, let's look at what's happening here. We want it to show greater than 2. So it either will show greater than 2 or it won't. That'll be our success and failure. The trials are independent, so each time that I roll the dice, the previous roll doesn't affect it. And the probabilities are constant. So we know that each time we roll a dice, the outcome has a given probability, and that's not going to change no matter how often we roll it. So again, let's note our values. So n is 12 and r is 8. When I think about the possible outcomes on an individual roll being 1 to 6, the chances of getting greater than 2 are 4 out of 6. So now I have my P and Q values. I'll fill my formula in. Again, I won't round off because it isn't asked for in the question, so I'll give all my decimal places in that solution. In our next question, we have a student taking a multiple choice test, 4 possible answers for each of the 10 questions, and we want to see if they just take a chance at randomly answering, what are the chances they'll get full marks. So since they're effectively guessing, whether they guess correctly or incorrectly in each question won't affect the result of the next one. We'll note our formula, we'll note our values. There are 10 questions. We're looking to see the chances of getting all 10 right. Chances of getting any individual one correct is 1 in 4, and chances of failure is 3 in 4. So we fill that in, and my result is 1 in, quite a big number there in the bottom, 1,048,576. So quite unlikely. Again, we're not specifically asked for a fraction or decimal presentation for the answer, so we're flexible in that. We can give whichever we like. Question 6 looks really like the question 2 that we had before. It's the same diagram. In fact, we've got the 5 counters in the bag again. A counter is selected at random 3 times and not replaced. We want to find the chances that a green counter is selected twice. But now the question actually says, explain why binomial distribution is not appropriate in this question. Can you suggest an alternative method? So first of all, why is it not appropriate? Well, there's a crucial difference between question 2 and question 6. Have a quick glance at it and see, can you figure out what that is? So in question 2, we're told that each time a counter is selected, it's replaced, but in question 6, it's not replaced. And as a result, that means that each event is, or each trial, if you like, is affecting the subsequent one. So we're finding in this case that our trials aren't independent as a result, and the probability of success or failure is going to change because of that lack of replacement. And then we're asked for an alternative approach. Well, combinations is going to be a handy way of working this one out. So let's think about what the question involves. We want to take 3 counters out of this bag. We want 2 of them to be green. So one is going to have to be something else. So let's think about the number of favourable outcomes in that case. From the 2 available green counters, I must choose 2, and from the other 3, I must choose 1. Now let's consider how many possible outcomes there are. Well, there's 5 counters altogether. I want to choose 3 of those. So I'm going to say 5 choose 3. And then off to the calculator and type that in. And I'm getting an answer of 3/10. Just note, in this type of approach where we use an NCR or combinations, there's an assumption as part of that calculation that there isn't any replacement happening. Now, the questions on the back of this sheet look very like question 1 to 6, but there's a little bit of variation here. Question 7, we've got a teacher connecting her device to the Wi-Fi in her classroom at the start of each of 9 lessons. Does this sound familiar to anyone? The chance the device successfully connects is 70%. Find the chances that her device successfully connects for the 6th time in the 9th lesson. So you can see here we're focusing in on one specific event here at the end that we need to consider. We want the 6th successful connection to occur at the 9th lesson. So what that means is I need to take the first 8 lessons and consider them as a group, and then take the 9th lesson by itself. So I want something to happen in the first 8 lessons, and then I want something to happen in the 9th lesson. So whatever figures I get, I'm going to be multiplying there. I'm going to use Bernoulli trials or binomial distribution for the first 8 lessons. So I'm going to say, okay, there's 8 lessons, and if I want the 6th successful connection in the 9th lesson, that means I must have 5 in the first 8. And I'll note the probabilities of success and failure, and I can go to the regular formula for that. I won't work this out just yet. I'm going to write in next what I'm going to multiply by here at the end. So I want connection to happen in the 9th lesson, and of course the chances of that happening are 70% or 0.7. So having typed that into the calculator then, I get that probability. On to question 8. This time I've got 10 rows overall. I'm going to break this up into the first 9 and then the 10th row separately. So I've noted my values and I've filled it into my formula, and then of course I also want to get a 6 on the 10th row. Just note there again, even though they say 10 rows in the question, my n for the first 9 rows is 9. And I'm typing into my calculator, I get my solution. Again, note that I'm not rounding off because there's no request for it in the question, but if it does say to give a certain number of decimal places, then obviously follow that instruction. So in question 9 then, we are bottle flipping. So we've got the first 4 tries and the 5th try separately. So since we want the first success on the 5th try, that means we don't want them to succeed at all in the first 4 tries. So we'll fill our formula in and then multiply by the probability of that individual success in the 5th try, which gives me the solution. On to question 10. This time we have the first 3 shots and the 4th shot separately. I note my values, I fill in my formula, I times by 0.4 for success in the 4th shot, and I get 0.1728. Question 11. I'll note my values, fill in my formula, times by 0.78 for success for the 8th seed. So I'm getting a really small number this time, 0. and then 6 zeros, 27948. Okay, last question. So I've got the first 6 matches and the 7th match separately. I'll note my values, fill in my formula, and times by 0.43 for that 7th match. And just notice we want 3 successes overall. Why am I writing a 2 here? Well, it's because this is the 3rd success, and I want 2 successes only to occur in here. Off to the calculator, and there's our solution.